A so many kilogram mass hangs from a ceiling by a single rope. Find the tension in the rope. So there's our mass hanging from the ceiling. What's the tension in that rope? We start by drawing a free body diagram. mg, the weight, acts straight downward, and the tension in the rope acts upwards. And that's it. So now let's sum the forces in the up and down direction. It doesn't matter which way is positive, but you have to choose one way to be positive, so I'll choose up to be positive. Tension up minus mg down, and by Newton's second law, the sum of the forces should equal the mass times the acceleration in the up and down direction, in this case. Well, this mass is hanging at rest, so the acceleration is 0, so the tension is numerically equal to the weight. This could be a chandelier or a disco ball. Now we have the same mass, but now it hangs from two ropes, each having an angle of so many degrees above horizontal, and our job is to find the tension in each rope. Tension on the left, tension on the right. If the ropes are the same material and thickness, then the tension on the left is equal to the tension on the right when the thetas are equal. We're going to make this assumption. Furthermore, we're going to assume that the ropes are symmetric with regard to the weight, so we're going to rename those tensions as simply T. And then we proceed just like we always do. We draw a free body diagram. For the tensions, we're going to break the tension into a horizontal portion, which I'll call T sub x, and a vertical portion, which I'll call T sub y. And the way we would get those is T sub x is, of course, numerically equal to T times the cosine of theta. T sub y is T times the sine of theta. Well, let's sum the forces in the y direction. We have Ty going up, and another Ty going up, and an mg going down. So that's 2Ty minus mg, and that, according to Newton's second law, is equal to the mass of the object times the acceleration in the y direction, or in the up and down direction. Well, this mass is at rest, so the right side of the equation goes to 0, which leads us to 2 times T sub y is equal to m times g, which means, if we divide both sides by 2, that T sub y is equal to 1/2 m times g. If you look at the picture here, T sub y is numerically T times the sine of theta. Well, theta we know the mass, so if we then divide out by the sine of theta, we get that T is equal to mg over 2 sine theta.